Has homework got you stressed out? Feeling like you have no time to do the things you want? Are you currently enrolled in data abstraction and structures with Dr. Ganad? Doug, what are you doing?
I'm killing it.
Well, kill no more. Say hello to the Mystery Science Box 3000.
What's that?
The answer to all your wildest dreams. Simply put your homework in the MSB3K and just wait as our breakthrough technology does all of your work for you.
Gee golly gosh, what is this breakthrough technology?
Our scientists in Uganda have discovered a data structure like many before, the priority queue. Yes, with the Mystery Science Box 3000, the possibilities are endless.
Awesome, but how does it work?
Well, the MSB3K takes your homework and puts it into a priority queue. Each homework assignment is given a priority based on what percentage of your final grade it is worth. Then, with some voodoo magic, your homework is completed in order from highest to lowest priority.
Voodoo magic, huh? Sounds legit, but tell me about this priority queue stuff. Seems fishy.
You see, Doug, priority queues are much like stacks, and even regular queues, except that each item is assigned a priority as it is added to the queue. The trick is that only the item with the highest priority, called the root, may be removed. This is great because it allows the Mystery Science Box 3000 to assign a value to each item that is not inherently associated with the item, and then allows for the system to organize the items by the priority it assigns.
Wow, priority queues sure sound useful.
They really are, Doug. There are three common ways of implementing a priority queue, with a heap as an internal structure, a simple unordered array, and a simple sorted array. Like I already stated, there are only two methods that are used primarily in priority queues: insert and remove. The difference in these two methods is that with the three implementations, the O complexities of all three are quite different. With a heap implementation, the O complexities of both methods are log n. With an unordered array, the O complexity of the insert method is just constant. This is because whenever you add an item into the unordered array, it doesn't really matter where you put it, you just append it to the end, because they are already unordered. Whenever you remove an item from an unordered array, the O complexity is always linear. This is because all the items in the array are unordered, so you're never really sure where the item is. You have to iterate through each and every element in the array to find which one that you're looking for, the one with the highest priority, the root. The opposite is said for the ordered array, though. Whenever you insert an item into the ordered array, the O complexity is always going to be linear, ON. This is because you have to find out where you want to put the item in the array. The items are supposed to be ordered, so you must iterate through each and every item to find out where the item that is lower than the one that you're wishing to put in is. That way, whenever you add an item, it still retains its ordered characteristic. Then after you add the item, any items following later in the array have to be pushed back by 1. Therefore, even though you're only implementing up to where you find out where the item should be in the ordered array, you still have to go through the entire array of length n to make sure that everything still stays in order, and that you also have the elements at the end of the array. This makes it very simple to remove an item from a sorted array. This is because you always know that the item with the highest priority is going to be in the front of the array. So, the remove method always has an O complexity that is constant, O of 1. Obviously, the heap implementation is much more efficient than the other two. This is because a heap has two very important characteristics. First of all, a heap is a complete binary tree, meaning that all of its levels are full except the deepest level, and even then, all elements are as far left on the tree as possible. Also, each parent node must be greater than or equal to its two children. This means that the item with the highest priority is always found at the root. Whenever you insert an item into a heap, the item is placed in the deepest level at the farthest left open spot for a node. Take, for example, adding your take-home exam to the priority queue. The final exam must be placed below A20 in this heap, but since the final exam has a priority of 30, and A20 has a priority of roughly 1, the two must be swapped. Once the final exam is the parent node of A20, it is also now the child node of the final project. The final exam still has a priority of 30, and the project has a priority of 15. Since 30 is obviously greater than 15, the two must be swapped also. Now the final exam is the root. Dequeuing from a heap is also the same as a priority queue. When removing an item from the heap, you must remove the root, the object with the highest priority. Then you take the item found at the deepest level at the farthest right filled node of the tree and place it at the root. In our previous example, we removed the final exam from the heap since it has a priority of 30 and is at the root. Then you take the deepest and farthest right item of the tree and place it at the root, in this case, A20. Then you test to see if the children of the new root have a greater priority than their parent. If one or more of them is greater, then you swap the child with the greatest priority with the root. In this case, you swap A20 with the final project. You repeat this process until there are no children greater than the item swapped. And then in this example, A20 has no children, so the method is finished.
Oh wow, that makes a lot of sense now. I can think of tons of examples where priority queues show up in everyday life. For instance, amusement parks that have lines with VIP members, and bandwidth management for routers.